everyone, I am Rishikesh Kulkarni. Welcome to my channel. In this tutorial, I am going to discuss about second chapter of the design of machine elements. The name of the chapter is design of simple machine elements. Some elements or some components which does not transmit any kind of motion or power amongst them, then such components are known as simple machine elements. In this chapter, I am going to discuss about the design of some components such as joints, that is cotter joint, knuckle joint and turnbuckle, levers, design of offset links. So I'll start with the design of joints first. In the design of joints, I'll discuss about the cotter joint first. The cotter joint is a type of joint which is used for joining the rods which are subjected to either tensile load or compressive load, and these rods are joined together by means of a cotter which is used for fixing two components, namely socket and spigot. One rod is tied to the socket and other rod is tied to the spigot. This figure indicates the sectional front view of the cotter joint assembly. It is necessary to understand the assembly of cotter joint. The cotter joint consists of mainly four parts. First one is the rods, second is the socket, third is the spigot, fourth is the collar. One rod is tied to the end of socket and other rod is tied to the end of spigot, and socket and spigot are fixed by means of a metallic plate which is tapered at one end. This metallic plate is known as cotter. Let D be the diameter of rod which is in the cotter joint, D1 be the outer diameter of the socket, D2 be the inner diameter of socket or diameter of spigot, then D3 be the diameter of collar for the spigot, D4 be the diameter of collar provided at the socket, L is the length of cotter, C is the distance of slot end on the socket from the collar end of socket, and A is the distance between spigot end to the slot end provided on the spigot. T2 be the thickness of spigot collar, and small t, which is not indicated in the diagram, but small t is the thickness of cotter which is fitted in the cotter joint. These are some various dimensions which are used for representing the various parts of the cotter joint. The spigot is the first component in the cotter joint to which a rod which is either in tension or in compression is attached. This diameter of spigot is indicated by D2 and the diameter of collar of the spigot is indicated by D3. The thickness of collar, this thickness of collar is indicated by T2, and the distance of this slot end to the spigot end, this solid portion, is indicated by A. This slot is provided in spigot for accommodating the cotter in the spigot. The next component is the socket. Socket is the another component in the cotter joint which is used for attaching the other rod which is either subjected to tensile force or subjected to compressive force. The outer diameter of socket is indicated by D1. The diameter of collar for the socket is indicated by D4. The distance of the collar end to the slot end, this distance is indicated by C. Next component is the cotter. Cotter is the tapered metallic plate which is tapered one of its side. The taper provided on the cotter is 1 mm is to 8 mm or 1 mm is to 24 mm or 1 to 48. The taper is provided on the cotter is because it increases the degree of tightness for holding the spigot and socket against the externally applied load, and also it helps for easy withdrawal from the joint when the joint is to be disassembled. The cotter in the cotter joint is subjected to two types of forces. First one is the double shear stress and second one is the bending stress. Now we will discuss about the strength equations for each component, that is socket, spigot and cotter. The strength equations are nothing but the equations of stresses. The general equation of stress is load is equals to area into stress, or stress is equals to load upon area. To get the strength equation of any component, we need to know the type of stress induced in the component and the area on which the stress is induced. There are common stresses which are induced in the spigot and socket, namely tensile stress, shear stress and crushing stress. So we'll one by one see those stresses induced in spigot as well as in socket. The tensile stress induced in the spigot is at the weakest portion of the spigot, that is where the slot is created, and it is indicated by section 1.1. The tensile stress induced in any component acts on its cross-sectional area. Next, the next type of stress is shear stress. The spigot and socket is subjected to double shear stress. The shear stress developed in the spigot is in the portion from slot end to the spigot end, which is indicated by a small letter A, and in the diameter of spigot. That means area under stress will be A into D2, that is diameter of spigot. The next stress induced in the spigot is the crushing stress, which acts at the contact area with cotter. So thickness into D2 will be the area under the crushing stress. This is for spigot. The stress equation is equals to load is equals to area into stress. Load is, we are assuming that the spigot is subjected to tensile load of P kilonewton is equals to area pi by 4 d2 square minus d2 into t multiplied by stress, that is sigma t, tensile stress. Next, shear stress. The shear stress acts on the portion that is from end of slot to the end of spigot, which is indicated by a letter small a, and it acts throughout the height of spigot, that is diameter of spigot. Therefore, the area under stress will be 2a into d2. This tau I have written by mistakenly over here. So the area under stress is, as the spigot is under double shear stress, therefore the area under stress will be 2a into d2. Okay, and the stress equation or strength equation will be load is equals to area into stress, which is nothing but the P is equals to 2a into d2 into tau. Next and last type of stress induced in the spigot is crushing stress. The area under crushing stress is this thickness of slot and length of cotter which is in contact with spigot. Therefore, the length of cotter which is in contact with spigot will be equal to its diameter, that means d2. Therefore, area under crushing stress will be T into d2. The stress equation or strength equation for the crushing stress of spigot will be then load is equals to area into stress. Load, that is P, is equals to T into d2 into sigma CR. So this is about the strength equation for spigot. So next we'll discuss about the strength equations for socket. The socket is also subjected to same stresses to which the spigot is subjected. The tensile stress in the socket is induced at the weakest portion, which is indicated by 1.1. The shear stress induced in the socket in the region that is from end of socket collar to the end of slot, which is indicated by small c. The crushing stress induced in the socket is at the slot which is provided on the collar of socket. The area under stress for the crushing stress is thickness of slot or thickness of cotter and the portion of length of cotter which is in contact with socket or socket collar, which is nothing but the outer diameter of socket collar, that is d4, minus inner diameter of socket, that is d2. To find out the strength equations for socket, we need to find the areas under stress. The diagram for areas under stress are given over here. Any stress induced on the solid portion of the component. Therefore, we need to find the equation for the solid portion of the area. For tensile stress, the solid portion of the area will be the cross-sectional area of the ring minus the area for hollow portion, that is the slot provided for the cotter in the socket. Cross-sectional area of the ring will be pi by 4 d1 square minus d2 square minus area of hollow portion, that is area of slot, which is d1 minus d2 into t. Therefore, area under stress will be pi by 4 d1 square minus d2 square minus d1 minus d2 into t. Ultimately, the strength equation or stress equation for the socket which is subjected to tensile stress will be load is equals to area into stress. That means P is equals to pi by 4 d1 square minus d2 square minus d1 minus d2 into T multiplied by sigma T. Here the d1 minus d2 into T is the area of hollow portion which got subtracted. The area under shear stress, as the socket is also subjected to double shear, will be 2 into d4, that is outer diameter of collar, minus d2, that is inner diameter of socket, into C. Therefore, the strength equation for shear stress is load is equals to stress into area, which is nothing but P is equals to 2 into d4 minus d2 into C multiplied by tau. The crushing stress which is generated in the socket due to the reaction of cotter coming onto the slot of socket. Okay, the area under crushing stress will be then d4, that is outer diameter of collar for socket, minus inner diameter of socket into T, that is thickness of slot. The strength equation or stress equation for the crushing stress of socket is given by load is equals to area into stress. Load, we are assuming it is a P kilonewton, is equals to d4 minus d2 into T multiplied by sigma CR. Now we will discuss the strength equations for cotter. The cotter is subjected to double shear stress and bending stress. So first of all we will see how the cotter is subjected to double shear stress. When the cotter is fitted in between the socket and spigot, then the portion of cotter which is fitted in spigot will try to get pulled in right side, and the portion of cotter which is fitted in socket will try to get pulled in left side. Therefore, the cotter will try to get sheared off into 3 pieces. This occurs due to the double shear stress developed in the cotter, and this shear stress is acting on the cross-sectional area of the cotter. The cross-sectional area of the cotter is given by mean width multiplied by thickness of cotter. Therefore, the area under shear stress, as it is a double shear stress, will be twice B into T. Hence, the strength equation for the cotter will be P is equals to 2 into B into T multiplied by tau. The next type of stress in the cotter is bending stress. When the cotter is get loosely fitted in the socket and spigot, then instead of shear stress, it is subjected to bending stress. The portion of cotter which is enclosed in the spigot will be subjected to uniformly distributed load, and the portion of cotter which is enclosed in the socket will be subjected to uniformly varying load. If we find the equivalent point loads of these forces, then these forces will act eccentrically horizontal axis of cotter, and due to this the cotter is subjected to bending moment and bending stress. If we take the moment of these forces about the horizontal axis, then on right side the moment will be P by 2 into d2 by 2 plus x, where x is 1/3 of y. The y can be calculated as d4 minus d2 divided by 2. Therefore, the value of x will be d4 minus d2 divided by 6. And if we take the moment in the left portion of cotter, then the moment of forces will be P by 2 into Z. Therefore, the total bending moment acting on the cotter will be M is equals to P by 2 into d2 by 2 plus x minus P by 2 into small z. Value of x is d4 minus d2 divided by 6, and the value of z is assumed that it is taken as 1/4 of d2. Therefore, this is the equation of bending stress acting on the component. As the cross section of cotter is rectangular, the equation of section modulus capital Z will be equal to I by y, that is 1 by 12 into TB cube divided by B by 2. Hence, the equation of Z becomes 1 by 6 into T into B square. Therefore, putting the value of bending moment and value of capital Z in the equation of bending stress, sigma B is equals to M by Z, will get P by 2 into D2 by 2 plus D4 minus D2 divided by 6 minus P by 2 into D2 by 4 whole divided by 1 by 6 into t into b square. After simplifying this equation, we'll get sigma b is equals to p by 2 into d2 by 4 plus d4 minus d2 divided by 6 whole divided by tb square divided by 6. So this is about the strength equations of cotter. Next we'll discuss the design procedure of cotter joint. The design procedure of the cotter joint is in 4 to 5 steps. In the first step, we have to design the rod which are either subjected to tensile stress or compressive stress. Therefore, the diameter of rod can be found out by following equation, which is load is equals to, that is P is equals to pi by 4 d square into sigma t, where d is the diameter of rod and sigma t is the tensile stress induced in the rod. In the step 2, we have to design the spigot. The spigot can be designed by two ways, either by empirical equation or by strength equation. If you are using the empirical equations for designing the spigot, the diameter of the spigot, that is d2, can be taken as 1.21 times the diameter of rod. The thickness of slot in the spigot for accommodation of cotter is taken as 0.31 times diameter of rod. If we want to design the spigot by strength equation, the diameter of spigot can be found out by considering that spigot is subjected to tensile stress. The equation for the tensile stress is given by P is equals to pi by 4 d2 square minus d2 into t into sigma t. From this equation, you can obtain the diameter of spigot or inner diameter of socket. If you find the diameter of spigot by empirical equation, then it is recommended that you have to check the tensile stress induced in the spigot. The tensile stress induced in the spigot can be checked by putting the calculated value of d2 in this equation and putting the value of load acting on the spigot. Then you have to calculate the value of sigma t. This calculated value of sigma t is then compared with the allowable stress which is given in the problem statement. If the value is less, then the design is safe, and if the calculated value is greater, then the design is not safe. So for that, you have to find the new diameter by using this equation. Next, the diameter of spigot collar can be found out by following empirical equation, which is given as 1.5 times d, that is diameter of rod, and the thickness of collar for the spigot is taken as 0.45 times the diameter of rod. The distance between slot end to the spigot end, which is indicated by small a, is given as 0.75 times diameter of rod. Next, after calculating all these dimensions, finally you have to check the shear and crushing stress induced in the spigot. The shear stress can be checked by following equation, which is P is equals to 2 into A into D2 multiplied by tau. In this equation, you have to put the value of load, value of A and calculated value of D2 from the previous equations. You have to calculate the value of tau, which is then compared with the allowable shear strength of the material which is given in the problem. If the value is less, then the design is safe. If the calculated value is greater, then the design is not safe. After that, you have to check the crushing stress induced in the spigot. It is given by P is equals to T into D2 multiplied by sigma CR. Again, put the corresponding values of thickness and D2, that is diameter of spigot, in this equation, and you have to calculate the value of sigma CR, and you will have to compare this value with the allowable strength of the material. So this is about the designing of spigot. The next step, you have to design the socket. The socket can also be designed by two ways, that is by empirical equations and by strength equation. If you are designing the socket by empirical equation, then the outer diameter of socket, which is given by D1, is taken as 1.75 times the diameter of rod, and the thickness of slot in the socket is taken as 0.31 times diameter of rod. Next, outer diameter of socket can also be found out by strength equation by assuming that the socket is subjected to tensile stress. The equation for the tensile stress for the socket is P is equals to pi by 4 d1 square minus d2 square minus d1 minus d2 into t multiplied by sigma t. The diameter of collar for socket, which is indicated by d4, is given by empirical equation, which is equals to 2.4 times the diameter of rod. Next, the distance between the slot end of collar and distance between the slot end to the collar end of socket, which is indicated by C, is given as small c is equals to 0.75 times the diameter of rod. Next, after calculating all those dimensions, we have to check for the crushing and shear stresses induced in the socket. The shear stress induced in the socket is given by P is equals to 2 into d4 minus d2 multiplied by C into tau. Here you have to put the value of d4, which is calculated by this empirical equation, d2 which is calculated in the previous step, C which is calculated by this empirical equation, and putting all these values of P, d4, d2 and C in the equation, you will have to calculate the shear stress in the equation, and the value of calculated shear stress then is compared with the shear strength of material. If it is less than the allowable shear strength of material, then the design is safe. Likewise, you have to check the crushing stress induced in the component. The equation of crushing stress induced in the component is given by P is equals to d4 minus d2 into T into sigma r, and you have to calculate the value of sigma cr, which is then compared with the strength of the material. So this is about the design procedure of socket. In the next step, we will discuss how the cotter is designed. The cotter is also designed by two ways, by empirical equation and by strength equation. The empirical equations for the width of cotter is given by B is equals to 1.6 times the diameter of rod, and thickness of cotter is given by 0.31 times diameter of rod. If you want to find the cross section or the dimensions of cotter by strength equation, then it is assumed that the cotter is subjected to double shear stress as well as bending stress. The equation of double shear stress induced in the cotter is given by P is equals to 2 into B into T multiplied by tau. And when the cotter is subjected to bending stress, the equation of bending stress is sigma B is equals to P by 2 into D2 by 4 plus D4 minus D2 divided by 6 whole divided by T into B square by 6. So this is about the design procedure of cotter. By this way, we are completed with the design procedure of cotter joint. In my next tutorial, I am going to discuss about the design of knuckle joint. Thank you for watching my video. Thank you.